Okay, excellent. Hi, my name is Ridwan Alam. I'll be presenting today on autonomous driving object detection. First and foremost, thank you, DataPhilly, for hosting this event and letting me showcase my presentation here. And then thank you, Raman, and everyone else that helps put these together. So just in regards to my presentation, this was actually from the bootcamp that I just completed. This is my last and final project that I presented on. And I was just really curious about how does an autonomous vehicle see? So such as companies such as Tesla, Cruise, Waymo, Nuro, whatever other autonomous vehicle companies there are out there, just how does it work? And obviously some utilize radar and or LiDAR. Then obviously a lot of them will have cameras just to understand, hey, what is that across the road? Is it a car? Is it a dog? Is it a person? And the reason that's important is because, well, that information is fed back into the car. And then from there, it has logic saying, okay, there's a car here, don't take a turn into here. It's a very important step. So with that being said, I kind of wanted to build my own model just to be able to detect traffic signs, traffic lights, stop sign, and other vehicles on the road just to see, okay, how does this actually work? Like how does a car actually see other objects on the road essentially? So just to kind of get this started, and you know how they say a picture is 1,000 words? I like to think of it as more of 1,000 directions in this context. Let me show you why. So here we have a video of someone in Autopilot in a Tesla. And so a Tesla actually operates with a hydronet. So they have cameras that come to a neural net. And so as you can see, this is just showing 3 of the cameras. And it's picking up different types of cars. And then you'll see it'll detect people in a second here, and so on and so forth. And those are the boundary boxes that you see on the right-hand side. And so this is because this is feeding to the car and telling it, hey, like, don't take a turn here, or you can take a turn here and it's safe to do this, etc. So this is an extremely important step, just to kind of give you a little bit of context. So basically, this is kind of just a sum up as far as what I'm looking for. So we're just detecting objects, and we just want to see the eyes of the autonomous vehicle. Like, what does the car actually see? So for this model itself, we'll just be detecting traffic signs, lights, and other vehicles, and stop signs, which falls underneath traffic signs. And I'll explain later of why I broke that off into a separate class of its own. So as you can see on the right-hand side, so this is actually my model detecting on a video that I just fed it. And so as you can see, it's able to detect the other cars. And then obviously you have a false positive here where it thinks that speed camera is a traffic sign. So things to be worked on, but again, there's just MVP. This kind of something I want to understand. Okay, how does it actually work and how do we actually build this? So as far as building it goes, so we're going to need to use some sort of neural net. So for this one, I use a convolutional neural net called Darknet, and then real-time object detector called YOLO. Reason being, I just found a resource online and I saw that it was possible with it. And I said, okay, like, let me utilize this. And then just kind of going off of this example and then kind of customizing and catering towards what I want. So just to kind of break down what YOLO is, what other object detectors typically do. So here you have a sliding window. So this is basically a picture being fed into a model, and then there's a boundary box going over that picture. And the point of the boundary box is to predict or to understand, okay, where's the car? So as you can see, it's going over until it finds the actual car. This is very cumbersome. As you can tell, 1, 2, 3, 4, 5, it went over about 8 iterations before I realized, oh, this is where the car is. This is very inefficient. And so this would not really fly in a real-time situation, because imagine actually driving and then your car sees a stop sign, but now you have already gone past the stop sign and it 15 seconds later has said, oh, there's a stop sign. My logic says when I see a stop sign, I need to stop. So 50 seconds later, now it has told you to stop. And by this point, you've either hit somebody or something. Someone has hit you, or if by some luck you have gone by unscathed and everything is okay. This will not fly in a real-time scenario. So with YOLO, which stands for you only look once, and essentially what it is it breaks it into a grid segmentation. So it first takes the picture and then breaks it down into different blocks. And then you have the class probability map where it detects, and when I say different classes, I mean different objects within the image. So here you have a bike, you have a car, and you have a dog. So it thinks, okay, these are the objects or these are classes within this picture. And then it recognizes where all the images are or where all the objects are. So now it's drawing out boundary boxes and showing, hey, this is where all the objects or the classes are. And so it's showing the boundary box. And as you can tell, it's the dark black ones. And that's a little bit more bold, showing, okay, this is where the dog is, this is where the bike is, this is where the car is. And so when you combine it all together, because now it knows, okay, I think there's a dog here, I think there's a bike here, I think there's a truck here, and I think this is where it's located. There's the final product. So it's able to detect where the objects are, but then it's also able to classify where the objects are. And this is all done in one pass when the model is built. So this is very key because, again, you want instantaneous results, obviously, with autonomous vehicles. So now the question becomes, well, how am I going to even start to build this? So first and foremost, just like any other model, you have to feed it. You have to feed it information. And for this case, for this neural network, we'll feed it images. So with this being said, I collected images from Google Open Images of traffic signs, traffic lights, cars, and stop signs. And then I had my plethora of images, and I did about 1,000 to 1,500 pictures for each class. And then the other part was, though, okay, now you have these images. What do you do with it? Do you just feed it into the model? Not exactly. So now you have to label it. So there's an open source library you can use, or you can use other annotation tools. I use label IMG. And so what this essentially does is imagine a picture and then imagine a car within that picture. So your model will not know, your neural network will not know what a car is until you tell it what a car is. So in this case, I have the picture of the car, or a picture with a car in it. And then I show the boundary box, and I draw my own boundary box, and I show, okay, this is where the car is. And I show the X coordinate and the Y coordinate. So essentially helping it recognize, oh, this is a car within this image. And so it could be, I don't know, a Ford Mustang or a Toyota Camry, and then you have a side view, top view, front view, etc. So it starts to learn what a car is exactly and what types of car there is. So almost imagine a baby when he or she first starts learning and they're going through picture books, and you tell him or her, hey, this is a frog, this is a cow, and it's just iterating, and they're iterating, and they continue to iterate. So that's how this sorts works, where you just iterate over images over images over images. That's why I said I utilize 1,000 to 1,500 images per class. So it could just continue to iterate over the images, continue to iterate over the images, continue to iterate over the images, so on and so forth. So luckily for me, Google Open Images had already done that, where it had already set out all of the annotations. So then basically what you have is an image file and a text file, and the text file tells you the location of the actual object of the class. So then Google Open Images, luckily for me, had already done that. So I didn't have to go through. I had utilized a total of 5,700 images, 5,571 images. So I didn't have to go through all that. So I was lucky. All I had to do was eventually just feed the images and tell the model, okay, this is where you look at the images in the text file. And so I was good to go on that. The other thing was to ensure that I have a high average precision score, which I'll go over in a little bit. On my images, I used a pre-trained weights. So what this means is with Microsoft, they actually pre-trained 80 classes on different types of objects, such as humans, dogs, cars, etc. And so I could actually utilize a convolutional layer from there. So I wasn't utilizing the final weights, but just a cut of it where it was already trained on X amount of images. And so with that being said, my score would be higher if I just used a convolutional layer that was already trained on the images that I wanted to. Luckily for me, they had already trained on traffic lights, cars, and stop signs. That's why I decided to utilize stop signs for one of my classes, because it was already trained on it. So I said, okay, well, I want a higher precision score with the stop signs. Unfortunately, it was not trained on traffic signs. So that's going to have a lower precision score, and that's okay. Because again, this is more of MVP, and this is kind of what beginning iteration of it. So now that I have the convolutional layer that I want to use, and then now I have to specify certain parameters such as batch sizes, max batches, which tells, okay, how many iterations you want to go over, and etc. So now that I've specified my configuration file, I've told the model, okay, this is where my images are and text files are. I was ready to build my model. And so this is the final product. And this is actual video that I did record. I was not driving. My mother was driving. And so I was able to record this throughout our city. When I fed up the model, this is what happened. So it's able as traffic. Sorry, the connection is a little slow here. Recognize lights, and then recognize the cars. There you go. This is much faster. I think it might be slowing down my computer a little bit. And then it was able to recognize all traffic signs as well. And this is exactly what I wanted. I wanted to be able to recognize traffic cars. Perfect. A first time run through, it's not bad. I'm just going to check the chat real quick, make sure I'm not missing anything. So to just quickly answer the question that somebody asked, I did not utilize any other neural networks. I just did Darknet and YOLOv for this. So I'm sure you could build one utilizing TensorFlow as well or PyTorch. But for this one, I just utilized Darknet and YOLOv. All right, so now let's actually quantify the results. So I mentioned mean average precision score before. Precision, what does that mean exactly? That means when a model detects, hey, this is a car, I'm 80% sure that this is a car. And then same thing with stop signs. As you can see, it's a very high precision score. Traffic lights, 75%, that's okay. Traffic signs, as predicted, is going to be lower, so 42%. And that's okay. There was no convolutional layer that had been trained on traffic signs before, so my precision score was going to be lower. Now, the question is, how did I get to these precision scores? So this is where intersection over union comes in. So you see the ground truth boundary box, and that is my box that I had drawn out. Essentially, that's where I tell the image, this is what a cat is. Predicted boundary box, that's the model predicting, I think this is where a cat is. And so this is important because almost imagine a Venn diagram where you have the intersection. And so that intersection is your common of, okay, this is the overlap. And so the bigger the overlap, the higher the precision score. And so kind of showing you the mathematical representation over here. So you have the area over overlap, which is the middle part, and then the area over union, which is all of it. And so divide that by the other, and then you essentially get your precision score. And so throughout the training of the model, it was actually, the model would actually spit out, oh, at this point, the precision score is overall this, and of this for each class. So my precision score overall fluctuating from like 65 to 75%, again, being dragged down from the traffic signs, really. So that's the main parameter as far as not parameter, but result as far as understanding, oh, how is this quantified, essentially? All right, I want to look at the chat, make sure I don't miss any other questions.
I can read the questions back to you at the end of your talk if you'd like as well.
Okay. Yeah, sure. We'll do that. Sorry. Okay, so basically in conclusion, key takeaways, the objective is you want to increase your mean average precision score. So with that, I want to increase it for the traffic signs, specifically, obviously others as well. The other thing is I like to build more mobile app where I can detect that real time. And so with that, I actually had something. There's a little pre-built, and then I just deployed it on my phone, essentially utilizing Android Studio. And I just called it Dashcam with K to change it up. So this is real time. So this is actually detecting the cars, the trucks, and the traffic lights, as you can see here. So as you notice, there's a delay. So this would not be very optimal, but this is something that I would like to do with future models, with iterations of my future models, so that I can put this into an app and then be able to say, hey, my model is able to predict everything that I need. One thing that I actually want to leave with is, so my model was created with images, of everything that I had aforementioned. And so this is kind of cool because it shows that this is my drone footage that I took, and that it shows that it can actually detect other cars. And this is from an aerial view. So I didn't necessarily have photos of cars from an aerial view, but it's still robust enough where it's able to recognize the cars from an above, which is pretty impressive. Obviously, you have a lot of false negatives in the corner over there where the parked cars, they're not being detected, and that's something that needs to be worked on. And then you have false positive over here. Notice that park bench is a car and that tugboat is a car, which is not true. However, the reason I show this is because Joseph Redman, that actually created YOLO, he was approached by a military commander who said, oh, like, we actually utilize technology like yours. I don't know if he said YOLO exactly, but technology like yours for drone strikes, which is very scary, because what I did was kind of cool and fun, and autonomous driving, that's cool and that's fun, that's interesting. But with drone strikes, yeah, sure, that's innovative, but that's really scary. And so with that kind of brought him to a pause, and him to think about, wow, like, what I do is very impactful, and what I do actually can have a macro impact on society. And so with that, unfortunately, he has essentially bowed out from object detection or doing any of that. I think he said that February 2020, he would not be doing any more research on that. And so that kind of got me thinking about just a random quote I thought about was, just as technologists, we have a responsibility to be ethical in our work for the sake of society. Because what we do, and the reason I got into this was because, wow, like, the work I do here can have an impact. But obviously we have to be responsible as well, knowing that the work we do, again, can have an impact, kind of just reiterating that, because it can be positive or negative, and just to kind of keep that in mind and on the forefront, really. Obviously enjoying everything that we do, but understanding that what we do, well, I mean, it might seem kind of innocent at times, but at other times, I mean, the impact that it can have, we should be aware of that at all times. With that, I end my presentation and I open up to any questions. I am open for hire. I have been looking for work for the past couple of months since the conclusion of my boot camp. If you look at my name on LinkedIn, you'll find me. You can send me an email, and then you can go to ridwanalam.com to see my other projects. And please reach out if you have any questions. If you have work, obviously, or you're looking to hire, or if you have anyone I'd like to talk to, or if you just like to talk to me in regards to my projects, and just looking to connect, really, and kind of get more into this realm. Special thanks to the AI guy. I utilized a lot of his tutorials, and then Hung LC007 is a open source repo that I utilize, and that was very helpful. So with that, I conclude my presentation, and I will open up to any questions.
So let's start with the questions that were in the chat. Anne was asking, how does this work with detecting stopped vehicles?
Any thoughts on stopped vehicles? Yes.
Yeah.
So excellent question. I did not test that specifically, but I wouldn't see why it wouldn't be able to detect stopped vehicles. Obviously, from my drone footage, I didn't really understand why it wasn't like picking up the stopped vehicles in the corner, because again, all my images, the model is trained on still images of cars, so it should be able to pick up stopped vehicles. I didn't personally look into that, but that's an excellent question, and I should definitely run videos where it just shows stopped images. But yeah, it should be able to. I wouldn't see why not.
Okay. Next up, Jack was asking, in your initial video, there's one point where all the traffic lights have pretty solid certainty scores, and then there's one on the right that's pretty uncertain. And he was wondering if you had any thoughts about why that score was so uncertain.
That's a great question. I'm going to go back to that real quick, because I want to see that as well. 1 second. No. Good as this one here. Let's see. Just gonna pause it because it gets there. Okay, so here, okay, so we have 81, 83, and then 58% on that one, and then it's fluctuating. That's definitely a good catch. Excellent question. With that, I'm not sure. It could be a plethora of different reasons, because one thing is you definitely want to make sure that your image is very visible, so there's enough light. There seems to be enough light on the right side. So that's the only thing I can kind of think of. Maybe it wasn't picking it up properly, or maybe there's interference because of the other two signs on either side. Also, that's another thing. It didn't pick up the two signs, if you did notice, on this. So for some reason on the right side, it was having some issues. Not too sure. The only thing I can come up with is potential issue with the light being shed on there, but that's really it. And that's something that I need to look into.
Okay. Next up, we have some questions from Daniel. And he wanted to know if your precision score is only for objects that you detect, or does it take into account objects the model doesn't notice?
Oh, so the model only takes into account the objects that it's detecting. So then as far, sorry, so it looks like cars only seeing either traffic lights or only cars. Is it doing that on purpose? Chance is it only for objects that you can detect or take into account? Yeah, so that's actually, because the thing is, like, I guess in that regard, I would need to look more into the recall score as well, and that's something that I did not calculate for this one. But yeah, it's only for objects that it is detecting. That is, and just kind of to kind of continue on to why there's a score of 111%, and that's something that's been asked before. That's something that I would need to research more later. I'm not too sure why it has an overconfidence of 102% or 111%. So that's definitely a good question as well. The video is choppy. It's definitely due to Zoom and potentially my internet connection, because typically it's completely smooth. So yeah, I apologize for that.
Okay, and next up, Cassandra was asking, is there a value to having bounding boxes that are rotated relative to the grid?
Is there a value to have in bounding boxes that are rotated? Sorry, I didn't understand. Rotated in the sense of depending on the shape of the object.
So, and for some reason it gave me the wrong name there. This is Charles. So rotate in terms of like you're finding like rectangles, relative to the overall grid of the picture. But if you had a car that was kind of at an angle relative to the picture, or a traffic light, or if your whole camera was set up so it's rotated relative to how everything else is aligned, I'm not as familiar with kind of this image detection world, but I'd love to know more about, if that's something that needs to be considered, or things like that about, different shapes instead of just rectangles, or just rectangles oriented differently.
Oh, okay. I completely understand. That's something I honestly different. Let me write that down. Angled rectangles. That's something that I had actually not considered, because and if anyone wants to kind of jump in that might have more knowledge about this, because all the images that I inserted, they're obviously just straight shot. The cars at it's not at a weird angle or funky angle or anything like that, and the traffic signs and traffic lights are just straight on. They might be like weird angle as far as from front to back, but it's not like you're not going to see a 45-degree traffic light or anything like that. Excellent question. What I would have to do with that is literally just take an angle video and see if my model is able to detect that. I think I want to say yes, because of the drone footage, and the drone footage was taken from a higher angle, right? So then the angle that it's seeing those cars, it's still detected. So I want to say yes off the back, but again, that's something that needs to be further tested. Good question though.
Hey, this is Jack speaking. Isn't that a part of the convolutional net itself? Is that the whole point is that it'll like rotate images and kind of change them just to throw it off and to still detect those objects?
I'm not completely sure about that. That's an excellent question. Convolutional layer, if it's part of it. It may be. I'm not too clear on that. I would have to look that up. But yeah, that potentially might be.
Okay, and then our last question from the chat was, have you deployed your object detection network on any other hardware other than your phone and your laptop? And in particular, any microcontrollers?
I have not. However, there's this, I'm not sure if anyone's utilized it, if anyone can see this, the M5V stick, or sorry, M5 stick V, and these are cameras that can actually do object detection. I'm pretty sure, I have not tested it yet, but I'm pretty sure I can deploy my YOLOv4 weights onto here. Might need to use some sort of tiny weights format because obviously this is just like a tiny camera. And then what I did with the app was I converted it to TensorFlow, and then I used TensorFlow light weights. So then potentially doing the same here. I haven't gotten to it yet, but this is able to detect objects. I'm just haven't loaded my model onto this camera.
Great, so that's it for the questions from chat, yeah.
Texas second alternate.
Yeah,
Okay.
Thank you so much. And thank you, Christopher, for helping out with the questions there. And yeah, I'm thinking maybe later, because we're going to be uploading the recording, maybe we could get the YouTube videos from you directly so we can load it up with it as a link. And then that way people can watch those smoothly after the fact. But yeah, technology is what it is with conference calls. We can only get so far. So thank you so much.
Yeah,
And
thank you
now,
so much.
yeah. And now we will turn it over to Dan Pfeffer.
Okay, cool. Thank you. Just give me one moment to set up here. Not be tiny. Not what I wanted. Okay, well, this is probably what you're gonna get then. Just ignore the top stuff. It should be fine then. Okay, so thank you for that. Thank you, Ridwan. So I'm gonna be talking about something a little less interesting in my mind, not a cool finished product that we have here, but this is gonna be talking about SHAP values, which are a way of doing feature importance in your machine learning models. This is really coming about from my job. I'm a data scientist at Eversana. I look at insurance claims. I build models to detect patients with rare diseases. And so a thing that happens is a client comes and they want to know, okay, why did it say that this patient had this disease? What about them made them go, oh, you have this rare disease? And we want a way to actually show that to a client. And in my just trying to figure out how to do this, thing I came upon were SHAP values. So in this talk, I'm going to explain why we care about feature importance and then work my way towards SHAP values and give you a little kind of demo of what they can do. So let's start at the beginning of why.
Oh, are you, sorry, I can't see your screen share.
Oh.
I just want to double check that you're doing that. Sometimes my Zoom messes up if it switches.
Can people see my screen?
Yes.
I'm sorry, I think I forgot to hit the button.
That's okay.
Okay, you didn't need to see anything for the talk. Sorry, I don't know how to, Chrome is being stupid with the presenter view, so you're gonna see the top of Chrome. Yeah, okay, so yes, the talk's understanding SHAP values for better model interpretation. So let's talk about why do we even want to interpret a model? The first idea, or the first kind of thing here is that you don't want a black box. Let's say you make your machine learning model, it does whatever you want it to do. Let's say I make a model that predicts the weather outside based on what I'm wearing. I want to know what's going on in there. I don't want it just to be a magical thing that spits out numbers. For starters, I want to see that the model is working, like, period. I want to have there are some assumptions I have going in about the data, and I want to see that reflected on the end. If I wear a rain jacket outside and the model says it's not raining, there's something wrong with that. Like, I need to see why that's happening. Another thing is that you want to see what features drive a model's results and by how much. So let's say my model is working correctly and it goes, I wear a rain jacket and it says it's probably raining outside. So I want to know, how much does wearing the rain jacket actually matter here? Is the fact that I'm wearing a rain jacket, or is it the fact that I carry an umbrella with me? Which one of those is pushing more? And then a third point, or the fourth point here, is to figure out why the model came to a conclusion for a specific data point. So not just in general, like you could build a model and go like, okay, in general, a rain jacket is going to be like 50% of your probability value is going to come from there. But that might be different if I'm also wearing sandals and, I don't know, sunglasses. Maybe it turns out that a rain jacket doesn't matter when I have that combination. So it would be good if you can do a thing where it can determine for specific data points why it matters, and then which is local, and then globally why things matter. So like I was just saying, for feature importance, there's a local interpretation and a global interpretation. Local is how the features impact the result for one specific data point, and global is how the features impact the result for general data points. So this picture, hopefully we can understand it here, is we can assume we just have some two-dimensional parameter space. We have these two different classes of objects, and we build a model that is trying to determine between the two classes. So if we look at this data point here, or just this region in red, and we could try to explain what's happening there. This would be a local interpretation. It would only take into account information around it. So that if you're at this like orange point, you can see that if the x-axis increases, you're eventually going to transition into the purple class. But it doesn't really see if you go far to the left that you're going to also go to the purple class. But if we can also then take a global interpretation where we look at all of the data, instead of just data around this point, we take into account everything. And you can see that, oh, if we move to the left, we're going to hit purple again. We also hit purple if we go down. And so there's different things you get at it by looking at it globally and locally. And so in the end, we're going to want to be able to do both. So now I'm going to give you some examples of some non-Chap techniques that you may already know. So here are some simple ones. Regression. Everyone knows how to make a just basic linear regression. You get the kind of thing, it's y equals ax plus bx plus cx. And if you make a model like this, just the bigger the values of a, b, c, and just any of your coefficients, the more important the feature is, because it's going to impact the result of the model, which is y, by more. And technically, it's the absolute value. And so this is going to work for linear, logistic, and multi-dimensional regression. So all of them just super simple. It just comes directly from reading numbers off of this. A little more complicated is going to be a decision tree, where a single tree is pretty easy to interpret, especially for a single data point. Here's for predicting how they're gonna get to work based off of just some conditions. It's easy to see that, okay, what's the weather like? Okay, it's sunny. How much time do I have? Easy to interpret that. You can also do some more complicated things by looking at the how the features affect the impurity of the tree, or trees if you're dealing with some decision tree, or sorry, some random forest or XGBoost type thing, which is something that isn't too hard to, I mean, it's something that's easy kind of to build and understand. It's just which features are better at splitting up your data points by what class they belong to. So those are a couple simple ones in quotes. And now here's going to be some model agnostic ones. I'm not going to go through all of them. I'm just going to kind of point them out because you might know them. And I want to point out for really everything for the rest of this talk, there's this good online book by Christoph Moldner, just really good for just model interpretation. So if you are at all more interested in this, please go read his book. It was really useful. So just some techniques people might know: permutation importance, drop feature importance, individual condition, conditional expectation, there's partial dependence plots, there's accumulated local effects, and one I think that's slightly more known than the others, local interpretable model agnostic explanations, which is LIME, which is just a really good local interpretation technique. So those are all non-SHAP techniques. Now let's work towards understanding what possible or what a SHAP value is. So to start that, we need to understand what Shapley values are. So Shapley values. These are techniques from game theory that were first developed by Lloyd Shapley in 1951. Okay, so I'm not a game theorist, so let's see if we can understand what's happening here. So we're going to imagine that we have a game being played with a coalition of players, where coalition is just a group of players. when they work together and they're cooperating in this game, the end result of the game, the payout is going to be greater than any of the individuals played by themselves. So we can imagine that it's, let's say the game is digging a hole. By myself, I can dig a hole that's 10 feet down. Player 2, they can dig a hole that's 8 feet down. But then what happens when we work together? Maybe we dig a hole that's 20 feet down. So by working together, we add an extra 2 feet. So now the question is, how do we attribute those extra 2 feet to the scores of the players? Did I do 12 feet of work and the other person did 8? Or did we both do 10? Or is it somewhere in between? So Shapley values are a way of trying to figure that out. And we can not be doing game theory here and instead be thinking about this in terms of machine learning and model building. So game here is really our model. The players are going to be the features in the model. The payout is really the model output. And the player score that I talk about is the impact of a feature on the model output. Excuse me. And I might kind of vary between saying things in terms of payout and players or model and features, things like that. So if I do, I'm sorry. And the goal here is to get how much a player impact or a player or feature impact. Excuse me, let me try that again. The goal is to get how much a player or feature impacted the game's or model's results. So we want to figure out how much are they actually contributing, which is really how important it is. So Shapley values start with these 3 axioms, which are symmetry, which are 2 features if they have or should have the same Shapley value if they contribute equally to all coalitions. So if you have 2 features that always do the same exact thing, they should have the same Shapley value. Makes sense? Dummy player, a feature that does nothing to change the model output regardless of which coalition it is added to, should have a Shapley value of 0. If this feature doesn't actually do anything for predictions, it should have a Shapley value of 0. It doesn't do anything, therefore it has no importance. And the third / kind of fourth is this efficiency / additivity, where all the Shapley values for each feature must sum to the total possible payout model output, which is really saying that in terms of the model building and feature importance, that all of them, actually, I'll explain this one better in a couple slides. It'll make more sense. So if we combine those 3 axioms together, we can actually come up with a unique value that kind of solves that, which is given here, which is the formula for a Shapley value. Phi, over on the left-hand side, is phi sub I, which is going to be the Shapley value for feature I. To understand the rest of the equation, we know that big F is going to be the set of all possible features or all players in the game. S is going to be a subset of features from F, not including feature I, because we're looking for the Shapley value feature I. Bars around X is going to be the number of features in feature set X, or the cardinality of X. And little f sub X is the payout or the model output when using feature set X. So I color coded this 2 ways because there's really 2 things to look at here. Actually, before we look at those, let's look at the sum. We are summing this over all possible feature sets that don't contain I. So any possible things. If we have 10 features here, we get rid of one of them because we're interested in that. So now we have 9. So you have to think of how all possible ways that we can get groups of those 9 features. We can have all of them individually. We can have groups of 2, groups of 3, groups of 4, and so forth. So that's what S is. Now we want to sum over all these possible permutations. The right-hand side, or the red part, is, I think, the part that matters the most. This is the marginal contribution of feature set I, or feature I to feature set S. So what this is saying is, in terms of models, we can imagine that we build a model using all the features in S plus feature I. And we want to see what the difference is between if we built a model using only feature set S. So it's really seeing how much does having feature I change the results that we're getting. Then the green thing here, which is a mess of factorials, if you know, I don't know, like discrete math or combinatorics, this is just keeping track of how many different ways we can arrange a group of S things out of a possible group of F things. Just combinatorics, it doesn't matter that much. But really, what this formula boils down to is just a weighted sum of marginal contributions of I. So let's actually see an example of this and see how it plays out. In the top left here, we have our game that we're playing. Let's, I don't know, pretend that this is players A, B, and C selling lemonade, and it's how much money they can make in an hour. Player A by themselves can get 40 bucks. Player B by themselves can get 50. Player C can get 60. Now we look at combinations. So AB is what happens when A and B are working together. We see that when working together, they get $95, which if you look, 40 plus 50 is 90. So there's $5 extra that they get by working together. You can look at all the combinations. And then we can get to the end where if all of them work, we get 160, which is actually 10 more than them individually. So the real question Shapley values is, how do we, who did the effort to earn that $10? Was it all player A, B, C, or somewhere in between? And then if it's between, how do we arrange it between them? Over on the right-hand side is us calculating the Shapley value for player A using the formula on the previous page, where if you can see or remember that this is just saying, we look at all feature combinations and we add I to it, and we then subtract the feature combination without I. So we can imagine our feature combination is nothing. There's no one there. So if we want to do the marginal contribution of I to that, it's going to be, or I in this case is A. So it's really just going to be 40 minus 0. The 1/3 just comes from how you do the combinatorics. Now we can look at B. So what happens when we have A and B? We have 95. Now we subtract and just see what happens when there's only B, which is 50, and you're going to get a 45 in there. Same thing with C, and same thing with B and C, where you have 160 when you have A, B, and C, and then you want to subtract 120 when you only have B and C. So when you keep track of this, keep track of the combinatorics, sum these things all together, because the sum was on the previous page, you get a Shapley value, or a weighted average marginal contribution of 42.5. So you can see over here that this was 40. So by working together, A really contributed an extra $2.50 to the lemonade game. Down here is a slightly uglier view of this, where instead of looking at a single value, it's doing everything at once. It's looking at all possible combinations of all features in each possible order, and it's writing out what happens. I don't want to go through this right now. I just want to point out at the bottom, if you actually do the math and find out what the Shapley values are for all three features, you see that for A, you get 42.5, which matches. B, you get 52.5. C, you get 65. So if you actually add them up, you get 160. So this is what the third axiom for the Shapley value thing was saying, that when you add up all of these, you really get the payout of the game. And you can see here that the additional 10 that we got, half of it went to C, so they got 5, and a quarter each went to A and B. So that's a basic kind of Shapley value example. Okay, so we did Shapley values. Now we can talk about SHAP values. Okay, SHAP values are Shapley additive explanations. SHAP. So the original paper for them was by Lundberg and Lee in 2016. So it's a pretty recent thing. You can go read the paper here. It's more technical than I'm going over, and it defines things in a slightly confusing way. But just know that the way it works is that it adds these three desired properties, the SHAP values on top of the axioms for Shapley values, and then you can get a tool for doing feature importance. I think for the sake of time, I'm going to ignore this right now. Just know that there are three properties that more or less overlap with the original axioms. And what you get when you do this is all of a sudden more or less the same formula as before. You can see that the real difference now is phi sub I is really now a function of f and x, where f is the model that you have right now, and x is the specific data point you're using your model at or on. Now everything else is the same. Same combinatorics, same thing over here, but now it's doing it at specific data points. So nothing different here. So the basic idea here is that SHAP values are really just Shapley values. They're applied to a given model and a data point. And for each data point that you have, you can calculate the contributions to the model score for each feature. So if you have 10 data points and 10 features, that means you're going to have 100 Shapley values. And when you're doing this, you're really trying to calculate this over here, which is the marginal contribution of feature I to feature set S. And that's not easy to do efficiently. Naively, the way that you would actually do this is, since it's adding a feature to a model, is to build surrogate models where it's, okay, I have this many features, I'm going to build a new model using them, and then you train that model, and then you have to run it at each data point. So that's can be bad and get really expensive really quickly. If you have capital F features, that means if you are required to train 2 to the F models. So once you start dealing with 100 features, that's going to become super ugly and really terrible. And in the paper that introduced SHAP values, they did introduce a couple techniques. Actually, I don't remember if it was the first paper or maybe additional ones, but right away there were techniques introduced for trees that sped this up dramatically. And then there are some deep learning models that there are techniques to speed this up. And then So you don't always have to deal with the terrible 2 to the F number of models that need to be produced. There are approximation techniques that can be used for just any given model, so you can use it agnostically, and it can still be better than 2 to the F using approximations. I'm not going to be talking about how they do that stuff here. I don't fully know, but just know it is a thing. And so from this, you see that we can get the local interpretation of a feature impact at a single data point, because this is really defined for single data points. And also, we're going to be able to get the global interpretation of a feature by averaging over how it affects each individual data point. So we're going to see this more in a bit. So right now, I want to give you a manual example of SHAP values and how we do something. So it's kind of like what we already did. And this is going to be the kind of thing where you do it once in school to see how awful it is, and then you are shown how to use the automated tool. So right now, let's assume that we have a model that predicts the salary of an individual using their age, gender, and job. So what am I? 29-year-old male data scientist. What do I make? So that's what the model is doing. And we want to use, okay, so now that we have this model, we want to predict how much each feature impacts the result for a specific individual. Okay, for me, how much did knowing I'm 29 years old impact the model? So the way that we're going to do this is we're going to start off by building a set of surrogate models for each set of used features. So that is what is here on the right. So we have this model, age, gender, job. It uses all 3 of them. And for me, it spits out 83K. Very nice. Now, to actually figure out how much any of these features matter, we need to build a power set of models with all possible combinations of features. So we built a model that has no features, a model that uses only age, gender, job, or uses combinations of them. And each of these here are for a specific person. So we're going to say this is for me. All these numbers are what happens when you feed my 29 male data scientist to the model. So this is only for me that we're looking at right now. So we want to find the marginal contribution of age to this. And so each one of these rows, if you can see, has one more feature, where the top row has 0, 1, 2, 3. And so we can see how adding age works directly. So adding age to nothing goes from 50 to 40. So it's bad that we added that. Going from gender to age gender, again, loses things. Job to age job, loses things. Gender job, age gender job, loses things. So naively just looking at this, age is not looking like a very good feature for me. So you can actually use the formula for the Shapley value, or the SHAP value, and it's written out here, and it's full glory, and it looks kind of messy. You can ignore that. You can just kind of focus on this thing down here, which should look kind of familiar to when we did this originally, where you can see that the going from nothing to age gives us this 40 minus 50 here with a factor of 1/3. You can see that things going from gender to age gender and job to age job have a factor of 1/6 on them, and going from gender job to age gender job has 1/3, which is kind of based off of how many pathways that you can take. So that's where the combinatorics is really coming in here. It's how to predict this. And if you actually go through all the math, which is not too hard to do, you can see that you get minus $11,000. So what we can see here is, for me, the 29-year-old male data scientist, this model thinks that knowing I'm 29 hurt my salary by $11,000. So that's how this works. So now that I showed you this messy calculation, you may be thinking, okay, what do I actually get out of this? That was messy and I didn't get much. But there are tools to do this efficiently and make cool plots, which is really what I am all about. So the example that I'm about to do is going to use the red wine quality data, which you can find at Kaggle, and it's going to be using the Python SHAP module. The idea was taken from a Data Science article. So what I did here was I just loaded up my Jupyter notebook. I loaded up the data for this wine quality stuff. It's in a CSV. It has, 11 features that are all numerical. It's trying to predict the quality of wine on a 0 to 10 scale. And what we want to do here is we want to build a model to predict the quality of the wine from its features. And then we want to see what features matter to the model and can we see anything interesting pop out of there. So first thing we do, we load up the data, we train a random forest regressor on this. Didn't try to be fancy here, just kind of did some basic things. I make a model, it trains. I see how good it is, has a mean squared error of, what is that, like less than 0.4, so not too bad. So now we have our model. Let's see what we can actually do with it. So the very first thing that we actually want to do is get the SHAP values. So this is using the SHAP the SHAP module for Python, which is, I think, a pretty good tool. It is by Lundberg and Lee, or at least Lundberg. So the person who made SHAP values made the module. So you should hopefully think it's correct. The way it works is that you have these explainers where you feed in your module or your model to it. And the explainer is really your set of surrogate models. So the example that we just did, there were 8 possible models. The explainer is filling in for that. For trees, it's there is a technique that is simple and fast to compute. So it's much faster and easier than having 8 separate models. There is this model agnostic version that is the kernel explainer rather than the tree explainer, which will require training some surrogate models, but less than 2 to the number of features. And then once you have this explainer, you can find the SHAP values for any set of feature values that you feed in. So here I'm just I'm feeding in the training data because there's more of it and it makes the plots look prettier. And then this thing that we get out of here, just what I call SHAP values, are the SHAP values, where it is an n by n matrix where n is the number of data points that we feed in here, and m is the number of features. So SHAP value ij is the SHAP value of feature I for data point, or no, feature j for data point I. So now we find all the SHAP values. What do we do with them? Now is when we get pretty plots. So this is a summary plot. What this is showing is for each feature, we want to see how much each data point contributes, or okay, let me try to rephrase that. For each feature and data point, we can show the SHAP value. And so each one of these dots here is going to be a single data point. So we take, let's imagine that there are 100 data points we have in the training set. So that means we should have 100 dots. Clearly we have more, but that's fine. And so each one of these dots is for a single data point, and the position on the x-axis is going to be what the SHAP value is for that specific data point for alcohol or sulfates or volatile acidity. So what feature it's looking at. And the color is saying how high is that feature relative to the other feature values. So red here means that it's a very high alcoholic content. Blue means it's very low. Red for sulfates is high sulfates, low sulfates, and so forth. And so you're going to have the same number of points for every feature here. So if there are 100 here, they're going to be 100 in the second line, third line, fourth line. And right away from this, you can see that there are some like clear correlations where the higher the alcohol content is, the higher the SHAP value is, and it's more positive. So you're saying more alcohol means better wine, which of course, who doesn't love more alcohol in their wine? Sulfates, higher sulfates lead to better wine. I don't know what sulfates do in wine, but apparently I want there to be more of them. And you can see that you have a negative correlation with volatile acidity and the total sulfur dioxide, things like that. You can see that as you go lower down, you start really, you see things that don't have much information. So for the citric acid here, you see that there's positives and negatives on both sides. They don't go very far away from the mean of 0. So the citric acid really doesn't matter. It's the things at the top of this plot that matter. It is plotted in terms of how much they matter overall. So it's kind of cheating that way, but you can see that they don't look like they matter compared to the things at the top. And you can see also that you get a global and a local impact of each feature by looking at this, where each individual data point or each individual dot is a data point. So of course you get the local impact, but just by looking at this thing, you get a global impact by just the correlation that you see and the fact that it goes further out than the other ones. But if that's not as much of a global impact as you want, we can do things such that you get a single value for each feature. So this is the second summary plot that you can do, where now all these features have a single value. The way that you get this is by taking the mean, or not the mean, you take the absolute value of every single like data point here, or in terms of their x-axis value, and then you average that. So it's just the mean of the absolute value of the SHAP values. And so what this is really saying is that it's trying to find what features have the most impact on your model. It doesn't matter if it's positive or negative. It just wants to know which features do the most impact, do the most, or have the most change on the model prediction. So this is the global thing. This is like, if I want to say one thing, I want to say alcohol is by far, or not by far, but alcohol and sulfates are the biggest contributor to if a model, or if not a model, if the wine is going to be good or not, because they clearly swing the result the most. So that is one thing you can do, but you can do some more interesting things. You can look at these dependence plots where Again, each data point is for or each dot is for a single data point. And we can actually see how different features relate to each other, how they depend on each other, hence the name. So these are a little to stare yet. It takes me a while to stare at them, but maybe you're better than me. So on the x-axis is going to be a feature. The color now is going to be another feature. So we have alcohol content being on the x-axis, sulfates being the color. And then the y-axis is going to be the SHAP value, at least a SHAP value for alcohol in this case. So we can see that when we have a lower alcoholic content, so like 9 to 11, it turns out that it's going to be more beneficial to the model to have lower sulfates. Because if we have lower sulfates, we get closer to, we get closer to 0 for the SHAP value, because negative SHAP values means that you're lowering the score of the model, which if you remember from the very beginning, or 2 slides back, normally higher sulfates lead to higher SHAP value and therefore a higher score. So we can see here that there's this dependence between these two features that didn't pop out by itself. And you can see the same thing over here when looking at volatile acidity versus sulfates, that if we're in this range of 0.4 to 0.8 for the volatile acidity, we want lower sulfate values so that we can have a higher SHAP value, where that dependence doesn't necessarily exist. Once we get below 0.4 for the volatile acidity, that feature kind of disappears, that it blends together. Same thing with the alcohol. Once you get the alcohol above 11, they just kind of, there's no real kind of correlation between them anymore. And then another thing we can do with them is the most local that we can get is for individual data points, we can see how everything impacts it. So these are called force plots. So we're looking at 3 different wines here in this case, and we want to see what features give the wine its final score. So like what does everything? So you can look at this wine right here. The way that SHAP values actually work is there is some base value, which in this case is going to be 5.653, and you're adding the SHAP values to it to get the final score. So you can see that like sulfates of 0.86 means that we're giving this positive value of however big this is, that's pushing it to the right. The sulfur dioxide content is pushing it to the right. The pH value is pushing it to the right. But the alcohol content, which is 9.2, which I think was low, is pushing it to the left, which means trying to make it worse. Chlorides are making it worse. So you can see like this. So it explains for each one of these why they get what they get. So you can see here for this one, it gets pushed over to 7.46 from the base value of 5.6. Down over here is a bad wine that is actually at a 4.26, where nearly everything has a negative SHAP value, which is just saying this wine is pretty bad. Nothing about it is trying to make it good. Yeah, so you can see all that. And just, I think I forgot to mention this, but the way the SHAP values are working is that in this case, since we're doing regression, the sum of the SHAP values for every single feature plus this base value will give you your final score. That is what this plot is showing. If you're doing something with not regression, but classification, you can still do this because you can be doing this on the probability that the model is predicting a class. So you can always use these SHAP values, even if it's not directly regression. So what did we actually find by using the SHAP values on this red wine? At the very top base level, we find high alcohol content is good, high sulfate content is good, low volatile acidity is good, low sulfur dioxide is good. But we found some interesting things that weren't immediately obvious if we were looking at just single features and what they did. We found some interesting dependencies where when you had volatile acidity in this range of 0.4 to 0.8, that we prefer a lower sulfate content than a higher sulfate content, where again, if we only looked at the single features and their global interpretation, we wouldn't see this interesting thing pop out. And then it also allowed us to look at individual wines to get specific scores for them and why they got what score they got. So again, if we're going all the way back to what I started talking about at the beginning, where I'm trying to predict patients with rare diseases, this allows me to go, okay, this patient saw a doctor 27 times about stomach problems within 3 days. That's what made them seem like they had whatever condition. So now let's just look at global takeaways. What did I want to get? What did I want you to get from this talk? So the SHAP techniques allow you to get global and local feature interpretation, which best of both worlds. You get both things for free, really. This can work on any type of model, so you don't have any issues with that. So again, at the beginning, there were some techniques that really only work on regression, some that only worked on the trees, but this just works on anything you feed to it. You can show interactions between various features, which a lot of feature importance techniques, they kind of just here's what the feature does, that's it. It has no impact with other features. Then this last one is not a real thing, but I just put it here just because, where there's a formal mathematical basis to these SHAP values that involves these axioms and these required properties, which a lot of other things don't have. They are techniques that work. And I'm not trying to say other things are bad. And I'm not trying to say that the SHAP values are better because of this. I am just pointing out that it has this formal definition that some people might care about. I don't personally, but it's there. Is a thing to note about it. And so, yeah, that is my talk. Thank you for your time.
Thank you so much, Dan. We had several questions come in the chat. Some of them refer back to some of the earlier slides. So
Okay.
I tried to make a note of when they were.
Oh yeah, sorry, I forgot to put the slide numbers.
That's okay. The first question, sorry. Melissa asks, it seems like it would be clear to say f sub lowercase f sub f rather than f sub s union I. I think it was in the first, yeah, it was in here. So maybe there's a difference I'm not spotting.
Sorry, hold on. I'm actually seeing if I can see the chat. Oh, there we go, chat. Okay.
It was at 6:55 was the question that was posted.
Thank you. That seems like it'd be clear to say f sub f rather than f sub s. Yeah, so those are different things. S is not f minus I. F is anything. So if I have 10 features, S will be 0 features. It'll be feature 1 by itself, feature 2 by itself, feature 3 by itself. It'll be all of these possible combinations. So like, it is not f minus I. Like it is every possible combination that you can think of. So like if you have 10 items, there are lots of different ways that you can arrange them, especially if you are not considering all of them at once. So that's why it's not just f minus I.
Great. The next question was further in the slides about the earning amount.
Yeah. So
yeah.
Oh, sorry. This is just coming from that the 50K is probably the average of the data set. So just if you have like a regression model that you're trying to make for this and you don't have any actual features in it, you will still have the bias value, which in this case, it probably found that the bias value was 50K. So that was most likely the mean value of the data set. Like if you have, so what it's trying to say is if you have no information about the person, you just guess that they make 50K and you're most likely, or that is the most correct you can be without any information.
Great. The next question from Brahma, as all combinations of features are considered, is there a limit on the number of features that SHAP can be applied on?
Theoretically, no. In practice, yes. So if you're doing something with like decision trees, so be it a decision tree, random forest, I don't know if XGBoost works, but it's based on them, then you can do techniques that'll make it so that you don't need to build all these surrogate models. So there's probably not a real limit to it, but if you are doing something that is not a decision tree and is not the specific types of deep learning that work, which I don't remember what they are, then you're going to be stuck with this 2 to the, or you're not stuck with the 2 to the F because there are the approximation techniques they use, but it becomes pretty bad pretty fast. I don't actually have, like, I can't tell you like 224, I can't tell you that, but like if you use the knot trees, you will run up to that in the hundreds, I'm pretty sure. I mean, it also depends on your computer and what you're running on, but I think you don't want to go more than 100, probably.
I'll come back to Leonard's question, but Danielle asks, is the average SHAP value similar to the beta coefficient in linear regression?
My answer to that is I have no clue. I do not remember what the beta value is. I am sorry about that. I can look it up later.
Okay, Leonard has a question on summary plot 2. Do the single numbers all sum to 1 over all the features, or it is just that a coincidence for how that graph on that slide looks?
Is a thing. I don't know. Let me try to think. So the SHAP. Yeah, that's a coincidence.
Thank you.
Rama has a couple other follow-up questions. How does importance from SHAP values compare to the feature importance generated by other tree models like random forest?
That's a good question that I don't have an answer to. I don't think there's a direct comparison between them. So like usual things with forest is you're looking at what is it, the Gini something or the information gain, which is really describing how pure your splits are in the decision tree. But this is nothing like that. So I don't know if there's a like way to really compare them, which I realize is a bad answer, but I don't know if there is a good answer.
If I may ask, basically, if you, for any of your test models, right, have you run the same thing like random forest and the SHAP values and then made a comparison like that to see the feature importance that random forest has generated to what you found with using SHAP values?
No, I haven't. I mean, I figure that they will look similar because feature importance will generally be feature importance. So like they will, each thing you do with feature importance, there will be variation between them. But if alcohol is important, alcohol is going to be important and the model should pick up on that. So it's not to say that they won't get similar results in the end. It's just they might get to similar results through very different pathways, which it would be a good thing if I had done that to compare just the usual like sklearn random forest feature importance. Yeah, but I do think it would look similar, but for different reasons in a sense than the SHAP values.
Did that cover your next question, Rama, that you had after that?
I forgot what was my next.
Oh, sorry. Is it possible to generalize the interactions between various features across all predictions / observations?
Okay, hold on. I need to picture that. Is it possible to generalize the interactions between various features across all predictions? Is that okay? So this is not looking at interactions. So you want a way of doing something like this, but with interactions?
Yeah, if you go to your slide on interactions, right, where you were showing for each single prediction, then you could say that the combination of these features, right? If you just move on to the next slide or something, there you go. So you had like individual features affect a single prediction.
Yeah.
Right. So this is really good to see at an individual level. But if we want to, even is it possible? Is just throwing that question, because that's what we are always trying to find out, like how do individual features contribute and how do the combinations of it contribute? So can that be generalized over the observations?
I mean,
over multiple predictions?
That is kind of what this is, because this is just taking for like, if we're looking at only alcohol. So if we look at the 9.2 here, or I guess the answer isn't 9.2, it's whatever this number is that's to the left, whatever the size of this thing is to the right. If we take the absolute value of them and average them, excuse me, after we do that averaging between all of them, we get this number here. So that's, I think, the closest thing, because that shows on average how much is that feature contributing to the model. It doesn't say if it's positive or negative, it's just period. How much is it pushing the prediction?
Okay.
Yeah, I don't think there is a better way of, I mean, yeah, I would need to think more about this if there is a better way. But as of right now, I think this is the contribution of really all of them at once.
Okay, thanks.
Yogesh asks, are there any more efficient methods that you have found that are computationally better than the SHAP method in interpreting a model?
Oh, of course. I mean, like the Chap values are inefficient if you're not doing trees, which the time that I've actually used SHAP values at my work, I've used not trees. I've used some ensemble of a bunch of different types of models. So it actually is like pretty inefficient and takes a long time to do this. So it's, where are we going? We're going back to the beginning. Here we go. Fast. Like you can do things that are faster, but then you get, in my mind, it's a different interpretation where like the partial dependence plot is you already have a model, and what you actually know, we're going the other direction. I have a little bit about those. Partial dependence plot, like, do we want that? No, we want ICE. ICE is really like you have a model, you pick all of your data points except for one and you keep them constant. Then that one data point, you vary the values and you see how it changes your results. So like that's computationally, that's not so bad. I mean, you can run this over all the data points you have and it shouldn't be that expensive to do. So you can do that and you can average all of these lines that you get together and you can get the partial dependence plots. Like it's not an inefficient way of doing this. Like there are techniques that you can do, but then you lose the ability to do these like dependence plots and these individual force plots. So SHAP values give you a lot of things. I don't know of other feature techniques, other feature extraction or feature importance techniques that give you all of these that are both global, local, and like dependence. But like, yes, you can always find something that's computationally less expensive. It just doesn't give you as much.
Great. And Yogesh also asks if you have a GitHub where we can try this code, or perhaps it's in a Jupyter notebook or something.
Yes, I don't know if I can just leave it with like the DataPhilly people. Can I just give that to you, the notebook and
Yep.
CSV? Yeah.
Yeah. We you know, if the presenters are okay with it, we share whatever material is available to share. So the YouTube video that we'll post in a couple days, as well as any slides or links or anything that are relevant, that would be helpful.
Okay, then yeah, I will give that to you. I mean, just so you're aware, the Jupyter notebook that I have is really just like, there's very little besides what I have here, but you are welcome to take it and play with it. And also, you can look at this link, the Towards Data Science article, where I got this from, because it's more or less copying them. But yeah, it will be available.
Great. Well, thank you so much. We are going to stop the recording now.